Hello all, this is the week 6 tutorial of NPTEL course Digital Circuits offered by Professor Shantanu Chattopadhyay. Myself, Sai Shubham. I am in my PhD second year. I am pursuing my PhD in Electrical Engineering from IIT Gandhinagar. So we will start today's tutorial. So this is the first question. And I would like you all to solve this, okay? I will give you about 3 minutes to solve this. Just once again, can you all confirm if I am audible?
Yes, sir.
Yeah, okay, thanks. Just to be clear, the question says that this is a JK flip-flop. So what input condition? The output will toggle. Okay. So this is actually a JK flip-flop, not a JK latch. So I will discuss the solution now. Um, like there is nothing to explain. When j equal to 1 and k equal to 1, this is the condition when your flip-flop, JK flip-flop, toggles output. Okay. So if q is, so basically qn plus 1 will be qn bar. Okay. If this is 1, it will be 0. If this is 0, it will be 1. Had the question been JK flip-flop, sorry, JK latch, in that case, you have an enable signal. Okay. So when enable equal to 1 and j equal to 1, k equal to 1, then you will have toggle. Okay. So that is for JK latch. And this is for JK master slave. Fine. So moving on to the next question. So what will be the output of SR flip-flop when S equal to 1, R equal to 0? So I will give you 2 minutes to think. So this is an easy question. If you let's make a SR flip-flop. So in this case, when S is 1, this is 1 and R is 0. Okay. So this is Q bar. So this is a NAND gate. So the out since this is 0, the output will always be 1. Okay, because Q dot 0 bar will be 0 bar equal to 1. So Q bar will be always 1. So this is 1. Mm, actually, there is some mistake. This should be Q. Actually, the input that comes here in this case is actually S bar and this is R bar. Okay, so if that is what we follow, this will be Q and this will be Q bar. So if S is 1, then this will be 0. This will be 0. If S equal to 1, R equal to 0, then this will be 1. Okay. So in that case, Q will be always 1. So if this is 1, then this output will always be 0. Okay. Similarly, if you flip it, S is equal to 0, R equal to 1, so that will ensure that Q bar is always 1. Reason that this is a NAND gate. Okay. So moving on to the next question. The circuit which changes from serial data to parallel data is, there are 4 options: counter, multiplexer, demultiplexer and flip-flop. So I will give you 2 minutes. So the correct answer is, one second. So the correct answer is demultiplexer. The reason is that, so A, first you have counter. So when you provide a clock signal, which is also serial, okay, serial in nature. So counter will basically look like this. We'll have series of flip flop, okay, and this will be your clock, and the output will be fed to. So let's look at multiplexer. So in case of multiplexer, what do you have? You have multiple parallel inputs, and depending upon switch, you have single output, right? Demux is basically the opposite of it, where you have single input and multiple parallel outputs, okay? And here is the switch to control. Flip flop is basically one single. Uh, this is your input, this is your output. You will have clock and reset, okay? So flip flop is not the answer, okay? Demultiplexer, you have single input and there are multiple parallel outputs, okay? So this is your answer. Multiplexer cannot be your answer, okay? And regarding counter, basically counter will serially perform the counting. So how will you feed the input data to a counter? So this is also not the correct option, okay? So the correct answer is demultiplexer, okay? So the next question is, the toggle condition in JK master slave flip flop occurs when. So I think I asked this question. This is a similar question. So the answer is J equal to 1 and K equal to 1. Okay. In this condition, you will have Q equal to 0. In this condition, you will have Q equal to 1. Here you have Qn plus 1 equal to Qn. Okay. So this is the next question. Which of the following is the correct output? Correct about D-type flip-flop. So I will give you 2 minutes to answer this question. No, actually, I have not shared the PDF. So today I was thinking of uploading all the slides. Okay. So let's discuss the solution. So a D flip flop. Here is your clock. So if you have any output D, and this is your output Q. Sorry, any input D. This is your output Q. So whenever, depending upon this, whether this is positive or negative, suppose there is a clock edge. So whatever data D is there, it will be transferred to the output. If it is 1, then the output will be 1, and 0, then the output will be 0. Okay. So answer A is the option A is the correct answer. B says that the output complement follows the input when enabled. So it says that Q will be D bar, which is not the case. C says that only one of the inputs can be high at a time. So D flip flop has only one output, but you can have Q bar as well. Okay. So it says that only one of the inputs can be high at a time, but it has only one input only, right? One input. So option C is also wrong. D says that output toggles if one of the input is high. So this is the case for T flip flop. Okay. So next question. So three T flip flops connected to form a counter. The maximum states possible for the counter is. I will give you 2 minutes to think. So let's discuss the solution. So a counter using T flip-flop will look like this. So since this is 1, for every pause edge, this is positively, so this is positive edge triggered, okay? So for each pause edge, this will go from 0, 1, 0, 1. Fine. Now this will have the opposite trend 1, 0, 1, 0, 1, 0. Okay. But since this is connected to the clock of second T flip flop, so one second. Let's make a timing diagram. The clock is going. Which is always triggered at pauses. Okay. So the output will be this is 0, 1. You have positive edge over here. Next positive edge will be here. So output, this output will be okay. So if you see the counter, mm, okay. The mistake was that the Q0 bar is being fed to Q1. Okay. So it will have negative edge. So we have to check at this point. So it will flip. So you can see the counter. This is 0, 0. This is 0, 1. This is 1, 0. This is 1, 1. Okay. So this is how using T flip flop you have counter. So since there are three flip flops, three T flip flops, it can go from 0, 0, 0 to 1, 1, 1, 0 to 7, which is 8 states. Okay. So I hope this is clear. I will move on to the next question. So in a JK flip flop, and Jn equal to 0 and Kn equal to 1, the output Qn plus 1 will be. I think I have discussed the solution of this as well. Okay. Actually, I had already discussed the solution, so this question is redundant. So whenever you have Jn equal to 0 and Kn equal to 1, so the output will be 0. Okay. So the only condition when it will act as a memory is when both Jn and Kn are 0. Fine. So this is the next question. The output of SR flip-flop when S equal to 0 and R equal to 0. I will discuss the solution now. This is actually a very simple question. So I hope everybody is following. Is the pace too fast today? If it is, so let me know. Okay. So this is S and this is R. So in case when S is 0, R is 0, then this point will be 1. This will also be 1. and this is Q, this node, and this is Q bar. Now the output will be 1 into Q bar whole bar, which is Q. Okay, and here the output will be Q with 1 whole bar, which will be Q bar. So this will acts as a memory. Okay, which means that Qn will be Qn plus 1. So this is very similar to JK flip flop. I will show how. In this case, what you have, so in case of JK flip flop, what will happen is that if this is 0, J is 0 and K is 0, what will happen? This is 1 and this is also 1, which is similar to your this case. So in that case also, since this is similar to the above case, it will also act as a memory. Fine. So nobody pointed it out, but in the question I have mentioned about SR flip flop, but I have explained using a latch. Okay. So will the explanation change if instead of flip flop, this is a latch? Technically, I should explain using a flip flop, right? The explanation remains the same whether it is latch or flip flop. Okay. Whether it is a latch or flip flop, that will that is determined by the clock. Okay. Otherwise, the it is independent of the inputs. Okay. The output clearly depends on inputs. It is independent of clock or enable. Okay. By independent, I do not mean that when enable is off, then the output will change. What I'm trying to say is that the explanation will still remain the same. Since it is easy to explain using a latch, I have explained it that way. Okay. I will move on to the next question. So the question says that a D flip flop can be made from a JK flip flop by making. So how can we make a D flip flop using JK flip flop? I will discuss the solution in 2 minutes. So let's discuss the solution. So as you can see that this is the truth table for JK flip flop. This is the truth table for D flip flop. Okay, this is for JK flip flop. And the interesting thing to note that when the output is 0 when J is 0 and K is 1. Okay, and in case here D is 0. Similarly, the output is 1 when J is 1 and K is 0. And here you can see that D is 1. So what we can write is that so D J is equal to D and K will be equal to D bar. So this is the answer. Okay, fine. So the answer is option A. I hope this is clear. Moving on to the next question. So when the transition of a circuit from one state to the next state occurs at a discrete instant of time controlled by clock, then the machine is termed as. This is a fairly simple question. So the correct answer is B. So a clock is used to synchronize all operations. So yeah, this is the answer. Hmm. So before this, I wanted to ask one question. Okay, let's solve this question. Okay, so given a clock signal and input and output, you have to tell which flip flop is this. I'll give you about 5 minutes to solve this question. So this is an easy question. I would like everybody to solve this. I will discuss the solution now. I hope everybody was able to do it. Since the question says, as in question you can see that there is one input waveform, only one is there, fine. And there is one output waveform, okay. So in case of D flip flop and T flip flop, you have only single input. So it can be either option C or option D. So let's look. So in the option, it says positive edge trigger. So let's mark all the positive edge. So here you have one. So these are posits because there is a transition from 0 to 1. Right? So in this posit, let's mark the input values. So you can see that this is 0, this is 1, then you have 0, then you have 1, again 0, again 0, and this is 1. So whatever the input is there, same is the output. This happens in D flip flop. So option C is the answer. Okay. Clear? So I would like another question now. Question. Hmm. So in SR flip flop, when S is equal to 1, R equal to 1, what is this state called as? Uh, Better question is, this we call as illegal state, illegal inputs. So what is the reason? The options are race condition, can't change state, C fixed memory, D none. So you are correct. You have mentioned that it is a forbidden state, but why it is like what is the actual reason behind it? So I will give you one more one more minute to think. Okay. Then I will discuss the solution. So I will help you with this. I will make the truth table of a SR flip-flop, okay? SR Qn, Qn plus 1 and Qn plus 1 bar. Fine. So when this is 0 and 0, so whatever is Qn, that will be your Qn plus 1 and Qn bar will be your Qn plus 1 bar will be Qn bar. In case of 0, 1, no matter what is your Qn, Qn plus 1 will be 0 and this will be 1. Similarly here you have 1 and 0. So in this case, this is known as forbidden inputs. You have some Qn, so what will be the answer? So if you make logic gates, you will realize that the output will be both 1. So I think I should discuss the solution. Okay. So for some set of inputs, you are getting a correct output where both are 1. So there is actually no problem with this output. This output is perfect. But the problem arises when we want to shift from 1 1 to any other input condition. Okay. So this transition from 1 1 to any other input, this transition is not possible. Okay. So once you reach S equal to 1 and R equal to 1, you will have a perfectly well defined output, but once you reach there, you cannot shift to any other input because that will lead to a condition known as the race condition. Okay. So I will show you how it happens. So once you have S equal to 1, R equal to 1, so this state, this position will be 0. This is also 0. Fine. I think I made a mistake here. Okay. Now you have Q bar over here and this is Q. So your output will be, so this Q output will be 0 into Q bar whole bar, which is 0 bar, which is 1. Here also you have 0 into Q bar equal to Q bar, sorry, 0 bar equal to 1. Okay. So far it's good. Now I want to make the output. I want the output Q equal to 1. From Q equal to 1, I want to make it 0. That case, S needs to be 0, R needs to be 1. Okay. So let's make the transition S equal to 0 and R will be 1 only. So in this case, what will happen? This will become 1. So the output will be, so here you have 1 as an input. So output will be 0. Now this 0 will make this point from 1 to 0 because initially it was 1. So this output will be 1. So where is the race condition then? Let me check again. So 0 and Q, it will make this 1. Similarly, 0 and Q bar, this will be 1. So 1 and 1. Now when you make this from 1 to 0, this will be 0 to 1, and 1 1 will give this output as 0, and this output will go over here. This is 0 0 0, this will be 1. Actually there was supposed to be race condition, when what will happen is that this is 1 0, then this will again go back to 1 and 0. So this continuous oscillation will happen, okay, and it won't be able to settle in any state. So this is what we call as race condition. But right now I think I'm making some mistake. I will get back to you later. Okay. So for the time being, let's move on to the next question. So this is the flip-flop converted from JK flip-flop is. So you have to answer like, what is this flip-flop? So just a couple of minutes. I would like to explain the previous question. Okay. So in this case, what I had initially said that any other. So in this case, only this transition is not possible. Okay. From 1 1 to 0 0, this transition is not possible. Rest of the transition is possible. Okay. So now if you have SR as 1 1, if you shift it to, so your output Q and Q bar, so they will be 1 and 1. Now if you make it 1 0, your output will be 1 0. If it is 0 1, your output will be 0 1. But the problem arises when you want to go from this state to memory state. Okay, 0 0. In that case, you have a race condition. Fine. So the problem is that mm, so in this case, initially it was 1 1. So this is 0. This is 1. Okay, and the output was 1. Now you made from 1 1 to 0 0. So in that case, this will be 1. This will be 1. So when both the inputs to a NAND gate are 1, what will happen? The output will be 0. So both the outputs will be 0. And here comes the problem. Since this node is connected here, so this one will now flip to 0. Similarly, this one was connected to Q, so this will flip to 0. So what do you have now? You have a 0 1 condition, and when the condition is 0 1, the output will be 1. So 0 1 0 and with 1 and bar. So this will be 0 bar, which will be 1. So, and once Q is 1, this condition is repeated, so the output will be 0. And when the output is 0, this condition is repeated, so you will have a pattern of 1 0. So it won't be able to settle anywhere. Okay, so that is the reason. Once you have SR as 1 1, you cannot go back to the memory condition, because this will create the race condition. Okay, you can definitely shift to other two conditions. So this was the reason. This is the explanation. Fine. So I will give you 2 more minutes, and then I will discuss the solution of this question. Okay. So I will discuss the solution now. So okay, this point is x, this is xy bar, this is y. Let's suppose this is a and this is b. So what is a? A is x dot xy whole bar, okay, which is x bar plus y bar, which is xy bar. B is y xy bar equal to y x bar plus y bar equal to x bar y. Okay, now let's make the condition xy xy bar x bar y. Okay, so this will be your j, this is your k. Okay, 0 0 0 1 1 0 1 1. So when this is 0 0, this will be 0, this is also 0, this will be 0 0 as well. Now here it will be 0 and this will be 1. Similarly this will be 1 and 0. Now so in jk, when these two are 0, this is memory condition, this is also memory condition, fine. And this is for q equal to 0, this is for q equal to 1. Now you can see that for these inputs you can say that x is s and y is r, so they follow the pattern of SR flip flop. Okay, so in that way B is the answer. Clear? And someone asked in the chat, like textbook for digital circuits. So uh, I'm not very much sure about textbook because I myself have not followed any, but uh, NPTEL lectures are actually very good. And if you want additional help, then you can follow digital circuits from uh, NESO YouTube channel. So there is one YouTube channel, NESO, NESO. So there he has very nicely explained all the concepts of digital systems and digital circuits. So maybe you can refer that. So this is the next question. The expression of X output of the following PLC circuit is. I will give you 5 minutes to solve this question. Okay. I will discuss the solution now. So in the question it asks for x, right? So in x there are this intersection point. Okay. So if you look at them, so the first one is a bar, b bar, c. The second one is a bar, b, c bar. Third one is a, b bar, c bar, and the last one is a, b, c. Okay. So this is the answer, which is which is option B. Fine. Moving on to the next question. So I hope there is nothing to. These are AND gates, right? These are AND gates, and this is OR gate. So initially we performed AND operation. This is AND operation, and then we performed OR operation. Okay. So the next question is a little big. You might have to uh, copy the question uh, in your notepad. So this is the circuit. We have two flip-flops, two D flip-flops, and here is the output, and here are the different waveforms. Okay. So you have to tell that what is the correct output waveform. Okay, given these are input waveforms. So I cannot put everything in one screen. Maybe let's see. Is this visible to everyone? So I will give you 5 minutes to solve this question. Okay. Those who are solving, please note that the flip-flops are not positively edge triggered, they are negatively edge triggered, okay? So one thing I would like to share with everyone is that if you're preparing for job interviews or internship interview, these are very typical questions. Whatever I'm telling you, whatever I have showed you today, these are typical questions they ask. And other set of questions that they ask is that they will ask you to convert one flip-flop into another flip-flop, okay? For example, if you have D flip-flop, so the question will be how to convert uh, SR flip-flop into D flip-flop or SR flip-flop into JK flip-flop, okay? So these are the standard interview questions. So you have about 4 flip-flops, right? SR, D, T flip-flop and JK flip-flop. So you must be aware how to convert one flip-flop into another, okay? You should know how to, you should know the truth table of all the flip-flops, and you should know the difference between latch and flip-flop, okay, for each one of them. And apart from that, they will ask you to make uh, counters, shift registers, okay, and a different kind of counters using flip-flops. So these are all standard interview questions for any digital uh, circuits company, okay. So by digital circuits company, like any company that deals with Verilog coding, okay. So they will ask you these kind of questions because when you will be doing Verilog coding, you will be asked to make different counters and circuits uh, using flip-flops only. So you must be aware. Can you explain the difference between flip-flop and latch? Sure. I think I will first discuss the solution. So the simplest difference between a flip-flop and latch is that uh, a latch is a level triggered device, whereas a flip-flop is an edge triggered device, which means that a latch is active when your enable signal is active. Okay, whenever your enable signal is 1, your latch can perform all the operations. If you give S equal to 0, R equal to 1, it will basically make the output 0. Okay, but whereas in flip-flop, this is an edge triggered. By edge, it means that whenever there is a transition of clock from 0 to 1, so in that transition only, your output will be registered. I will explain in detail later. Now discussing the solution for this. So you can see that this is a negative edge triggered, okay? So whenever there is a clock transition from 1 to 0, your flip-flop will be active. So in this case, there is 1 to 0 transition over here, here as well, here as well, here. Okay. The problem with latch is that whenever your enable signal is on, the device is active. For example, take this case. Suppose instead of clock, this is enable. Okay. So here you can see that enable is high, and you can see that there is a transition in x1 and x2. For example, this is 0, this is 1, and this is 0. I think that is not visible. I think it is better now. So you can that for duration, suppose it is for duration, your signal is on, and any flux in x1 and x2 reflect in both. Okay. Whereas in a case flip flop, only during this transition, okay, only during this transition, whatever is your whatever is your x1 and x2, that will be registered. Okay. It doesn't matter what is x1 and x2 before this edge. Okay. Only right at this point, at the edge, the value of x1 and x2 will be considered. Okay. So this is the benefit of a flip-flop, because in a very large circuit, what happens is that the output from, suppose you have combinational circuit 1. A combinational circuit is where you have a different combination of gates, okay, and gate or gate. So this is a combinational circuit. This is another combinational circuit. Fine. So even if you have same set of inputs x, y, z going into different combinational circuits, the output here, the output at this point, output 1 and output 2, cannot appear at the same time instant, because each gate will have a different delay. So maybe C1 takes T1 time to process output 1, C2 will take T2 time. So they won't appear at the same time. So what will happen is that if there is a circuit over here, the output will fluctuate. Okay. Suppose initially it was 1 1, fine, and the output was 0, but it took the C1 circuit more time to process, and later the signal came from 1 to 0, so the output becomes 1. So if you do not have flip-flops in your circuit, what will happen is that your output will keep on fluctuating. So this will actually create some problem, because you do not know that what is your exact output. This actually causes problem in time sensitive circuits, for example processors, or in hazard circuits such as for emergency alarm. You do not want your output to be continuous dependent on your inputs. Okay. So in that case, you need a flop instead of a latch. I hope this is clear. So now, so these both so x1 and x2 both are 0. So output should be 0. So W2 cannot be the answer. So W1 is 0 and W3, W4. Okay. The reason is that the output is going to an AND gate. Okay. This is an AND gate. So now at this point, x1 is 1 and x2 is 0. So output will still be 0. But here you can see that it has transitioned to 1. So this is also not possible. Okay. So this is correct. and this is also not possible. Similarly, this is 1, this is 0, so output should be 0. Here this is 1 and this is 1. Okay, both are 1, so output should be 1. So here you have a transition. So W3 is the answer. Okay. So this is another question. Like this was the question for week 4. Okay, and I think I was unable to answer it in time. So I will discuss the solution right now. So the question was the minimum number of 2-input NAND gates required to implement a 2-input XOR gate. Okay. So this can be done as, if you can see. So first you can have AB bar. Okay. Then you can perform NAND operation of AB bar and A. So A and AB bar NAND. This is A bar plus B bar whole NAND, which is A B bar whole bar. Fine. So here you will get, so this will give you AB bar whole bar. This will give you A bar B whole bar. And if you perform the final NAND, it will give you AB bar plus A bar B, which is your XOR gate. Okay. So the explanation, so my solution had the use of 5 NAND gates, but one of the students gave a better solution. So this was the solution, which has 4 NAND gates. Okay. Is my screen visible, or I just want to confirm that if everything on the screen is visible clearly.
Yes, sir.
Okay then. So this is another question. We have to identify the following circuit. So this is a very easy question. Okay. The answer is B. The reason is that you have one input, two select lines. Okay. So if you have two select lines, it cannot be decoder because you have an input. Okay. So decoder does not have any input apart from the select lines. So since there is an input, either it can be a demux or a multiplexer, but you have four outputs, right? So in multiplexer you have single output, but in case you have four outputs, so the answer has to be demultiplexer. Okay. So B is the answer. Fine. Moving on to the next question. So this is the circuit. Now you have to tell that what is A and B. So I will give you 5 minutes to think and solve. So I will discuss the solution now. So if you see that B is basically mm, 1, 2, 4 and 7. A is 3, 5, 6, 7. Okay. Now see clearly if you have three inputs, so it cannot be a half adder. It has to be a full adder. So we have to determine if A is sum, B is carry, or A is carry, B is sum. Okay. So let's look at B. If this is 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, which is x bar y bar z, x bar y z bar, x y bar z bar, x y z. Okay. Now I think we can club this together. It will be x bar y plus x y bar z bar, and we can club this together. It will be, see if you can see, this is x XOR y, and if you club this together you will find that this will be x XOR y whole bar times z. So if you combine this, it will be x XOR y XOR z, which is basically your sum. Now A is 111, 101, 110, and 111. So this is x bar y z, x y bar, x y z bar, and x y z. Taking z common, x bar y plus x y bar, and here this will be x y z bar. This is not z bar, this is z bar plus z. Okay. X y, which can be written as 1 x bar y plus x y bar plus x y 1 plus z. So anything added to 1 will be 1 only. So we can write as 1 plus z. So this will be z x bar y plus x y bar, taking x y here. So this is x plus y plus x y, which is x z plus x y plus y z. So this is basically your C out. Okay. This is your sum. So A is carry, B is sum. Okay. So the answer is C. Okay. So are you aware about static timing analysis? So I wanted to discuss this question. Okay. So static timing analysis is also a standard interview question which they ask. So this is one of the question of static timing analysis. So this question, so so I would like to ask, this is the circuit we have, okay? Yes, so this is the circuit we have. I will explain different parameters to you. This is T min, T max. So here you have a metal wire, so which will have some delay. So in some cases the delay will be less, in some cases the delay will be high, depending upon fabrication, right? I think previously I had explained that because of the fabrication irregularity, your chip may perform differently. Some chips may perform faster, some chip will perform slower. So that's why you have a different timing. Okay. So in this case, what you see here is that there is a minimum time and maximum time. Okay. So now you know that for clock signal to pass from this wire, there is a t minimum as 1 nanosecond and t maximum as 2 nanoseconds. So it won't take more than 2 nanoseconds, but anyway it will take 1 nanosecond to reach the signal. Similarly, you have t min over this wire, 2 nanosecond and 3 nanosecond. There is a buffer. Okay, this is a buffer. So this buffer will also take some time to process. So here you can see that there are all the different parameters. Fine. So this is a D flip-flop. This is a D flip-flop. And T clock to Q means that whenever there is a positive clock edge, it will take some time for data to reflect as Q. Okay, so that is the delay. So T clock to Q means the time it takes for the flip-flop to work so that it can give the output Q depending upon your data D. So the question that is there is that what should be the minimum time period of the clock so that there is no hazard. So by hazard, so there is no timing violation. Okay. So I will give you a little hint about what is timing violation. So is everybody fine with me giving you this question? Like this is a slightly different. Okay. So I have a flip-flop over here. So I have a suppose D flip-flop. Okay. This is D and this is Q. This is D. There is clock and this is Q. Okay. So let's make a clock. So this is the clock waveform. Suppose this is a positive edge triggered. Okay. So this is my point of interest. Now just a second. So now I want, so this is my edge, okay, edge of flip-flop, because flip-flop is positive edge triggered, so this is the pulse edge. Now for flip-flop to register a data D, so okay, this suppose my input is some data D, okay, and I want the flip-flop to register it, okay, so that data should be available before some time of this edge, okay, so minimum this much, so minimum this much is the time before which your data D should be available. Okay. For example, suppose this is my D. Okay. So it should be like this. Okay. So this is acceptable. If this is the minimum window. Okay. So beyond this, my data D should be available so that my flip-flop can register it. Okay. Suppose my data D is like this. If it falls inside this window, my D flip-flop won't be able to register it, even though this is my clock edge. Okay, this is clock edge, and this is my data as 1. So even though the data is present before the clock edge, the flip-flop won't be able to register it because it violates certain minimum time. Okay, so this minimum time is known as your setup time. So data that has to be latched into that flip-flop should be available before this minimum setup time. Okay, it cannot fall inside this window. Similarly, if you have some data D, okay, which is fine, it made transition from 0 to 1 and it is fairly beyond this minimum window. So there is no problem with this. Okay, so data is available. One, it is not transitioning in this minimum window. Okay, but the problem is that suppose as soon after the edge, so this is your edge, and as soon as after this edge, if the data changes, okay, so what will happen is that there may again arise some violation. So you need a minimum time after the edge, okay, before which your D input should not change. Otherwise, that flip-flop won't be able to latch the data. Same reason. So you want the data to change after this window. Okay. So this is a minimum time. This is your edge. This is your minimum time as well. Okay. So you want data to change after this minimum time and should be present before this minimum time. So this time after the edge is known as hold time. Okay. And the time before this edge is known as setup time. Fine. So if the data changes inside this window, there will be some violation. So I hope this concept is clear. You have to make sure that the data is available before the setup time and should be there for a minimum of hold time. Okay. So the question it says is that this is a very standard interview question. So it says that figure out if there is a timing violation, and if there is a timing violation, you have to tell what. So in this case, I have not given you the clock. Okay, clock signal has not been provided. So I won't ask you if there is a timing violation or not. My question will be like, what should be the minimum time period of clock so that there is no timing violation. Okay. So this is the question. I will give you about 5 to 10 minutes to figure it out. Okay. This does not require any concept of electronics. This is a simple maths problem. Okay. I have explained about different flip-flops. You have to make sure that for the different flip-flops, there is no timing violation. So timing violation will appear because this is a path. Okay. The clock is there and this is one path, and another path is this path. So clock will reach these two D flip-flops at different time. Okay. Ideally, they should reach at the same time, but since in this case it is reaching at different time, it can lead to some violations. Okay. The problem can be that suppose the clock to D flip-flop, this flip-flop reached earlier as compared to this. Now the data processing happened. Okay, and then this clock arrived. So in that case, there is some delay, right? I hope this is clear. What I'm trying to say is that if I'm providing clock, it should not happen is that the clock reached this T flip-flop and it processed, and then the clock signal is coming over here. If you're finding it a little difficult, you can tell me. I might skip this, or you can continue solving this problem. So just to ask you all, is the question clear? If not, I can explain again. You can give a comment if the question is not clear. I will try to explain it again. So the problem here is that this is a combinational circuit. This is flip-flop. This is another flip-flop. And you have a clock. Okay, there will be some delay. And here is a clock. Okay, so what we want is that suppose the output of this combinational block is 1. Okay, and this is 0. Fine. And there is a clock. So you want not able to figure out the answer. Okay, so I am explaining you. This is a simple version. So the problem is that this is a clock. Okay. Now I made a transition over here, and this transition reached here. So this 0, since this is a D flip-flop, this will go over here. And suppose the delay in the combinational block C1 is so less that this 0 propagates over here. Okay, and then this clock signal reaches here. So ideally this flop should register the previous value, which was this one, but now it will register a false value because this processing has happened. So this 0 will come, okay, instead of 1. So this will lead to some error. So so should I discuss the solution today, or you might need some time to think, and I can discuss the solution in the next tutorial as well. Because if I right away give the solution without you thinking, then it would not mean anything. Okay, fine. So you can copy this question. I will discuss the solution in the next session. So the session ends right now. If you have any other question, let me know. I am stopping the recording.